let's take a look at the Doppler effect. So the Doppler effect is the idea that if you have a source that's emitting waves and you have an observer who's observing the waves, then the motion of either the source or the observer will affect the frequency that is observed. Now, that all sounds kind of abstract and general. So let's look at a specific situation. Let's imagine that we have a moving source of waves. And these could be whatever kind of traveling wave you want. We'll talk about that a little bit later. But maybe there's sound waves, and the source is traveling here to the right. Well, if that's the case, then eventually, if we wait a while, we would see something like this. In front of the moving source, the waves will be bunched up, or rather, the wave fronts will be bunched up. And then behind the source, the waves will be spread apart, or rather, the wave fronts will be spread apart. Now, what that means is that if you have an observer who is standing in front of the moving source, right here, that observer will receive wave fronts that are closer together. That observer will receive a higher frequency or a smaller wavelength from the source than you would expect. Meanwhile, if the observer is behind the moving source, then the observer will receive longer wavelengths or lower frequencies. Now, how much lower, how much higher, don't worry, we'll get to the numbers later. But now let's think about a situation where the source is stationary, but we have a moving observer. So the source is stationary. Let's draw the wave fronts around this source. And now imagine an observer that is moving toward the source. Now, that observer, as it moves toward the source, it will encounter the wave fronts more rapidly than it would if it was stationary. If it's encountering the wave fronts more rapidly, then it's going to perceive a higher frequency. Likewise, if the observer is moving away from that source, then the observer will encounter the wave fronts less frequently, meaning that it will perceive a lower frequency and consequently a greater wavelength. Now, this phenomenon happens for all traveling waves, mechanical, electromagnetic, but the specific mathematical details are a little bit different for each different kind. So we'll write down the one for the electromagnetic wave. Okay, we can say that the change in the frequency divided by the frequency is equal to the change in the wavelength divided by the wavelength, which is approximately equal to V over C. Okay, so this is the expression that you get in the data booklet, and it takes a little bit of interpreting to figure it out. So first, let's define what V is. V in this equation represents the speed of either the observer or the source, whichever one is moving. And there's actually a little detail to that that we're going to investigate later, but just keep that in mind. Okay, C, that's the speed of light, or the speed of the electromagnetic wave. Over here, delta F, that's the change in the observed frequency compared to the emitted frequency. Down here, F in this equation is the original frequency that's emitted by the source. And then similarly over here, the delta F is the change in the observed wavelength compared to the emitted wavelength. And then the wavelength down in the bottom in the denominator, that's just the original emitted wavelength. So notice, this equation, it's not telling you whether or not the change in the frequency or the change in the wavelength are positive or negative. In other words, this equation doesn't tell you whether or not the frequency is going to increase or decrease compared to its original frequency, original wavelength. Um, so it doesn't tell you everything. You have to determine that based on the situation. Okay, now another little detail. Let's look at this little approximation symbol here. The reason why this is an approximation is that this equation, the dirty little secret about it, is that it only works when the speed is not near the speed of light. If you get really close to the speed of light, turns out that this starts to deviate from reality. So that's why we have to have the little wiggly approximate equal sign in there. All right. The other thing to consider in this is v right there. So v is either the speed of the source or the speed of the observer, except it's not quite that simple. V here is actually the speed of the object along your line of sight. So let me draw a little diagram here. Let's say that I have a moving source and I'm an observer. And the moving source isn't moving directly toward me or directly away from me. It's moving kind of off like that. Well, v in this equation is the component of the velocity that's along my line of sight. So let me draw that in. Here is v of the source, and here's my line of sight, a line that connects the observer, me, and the source right there. The component of the velocity along that line of sight, that is the v that goes into this equation. Okay, now knowing that, let's do an example. Let's say that we have a faraway star, and let's say that this faraway star moves directly away from us. Okay, so here's the Earth. Here's that star. It's moving directly away from us. We're going to, assume that the observer is on the Earth. Um, because the star moves away from us, the light received at Earth will have a greater wavelength than what was emitted by the star. Okay, we call this redshift, by the way. It's something that's observed out in the universe. It's really quite important to many areas of astronomy and astrophysics. Um, but anyway, so for this situation, we know that we must be receiving a wavelength that's longer, that's bigger than what the star emits. So that means that the change that we solve for in the equation, that delta lambda, change in the wavelength, we can find that, and then we know that the observed wavelength has to be greater than the emitted wavelength. So the observed wavelength has to be the emitted wavelength plus that change. Okay, now let's say that we have the opposite situation. A faraway star moves toward us. Okay, so let's draw that real quick. Well, in this situation, we must be receiving wavelengths that are smaller than what were originally emitted by the star. And this is called blue shift, by the way. This is also observed out in space in astronomy. So in this situation, we know that we should subtract the change in the wavelength from the emitted wavelength, the original wavelength, because the observed wavelength has to be smaller than the emitted wavelength. Okay. You can make a similar argument for the change in the frequency using this kind of justification. But in the equation, remember, you can solve for the change in the frequency, you can solve for the change in the wavelength, but you yourself must determine whether or not to add or subtract that to the original emitted wavelength and frequency. All right. So now we're going to move on to just the HL content. So that's the end of the HL and SL. Now we're just going to do HL content. So we're going to look at the equations that we get for mechanical waves. So waves that are not electromagnetic waves. So like sound waves, ocean waves, those kinds of things. And we're going to have two sort of branches here, two versions of the equation. One is for if you have a moving source. If you have a moving source, then this is the equation. F prime is equal to F times V over V plus or minus US. So F here is the original frequency that was emitted. F prime is the observed frequency. It's not the derivative. It's the observed frequency. The V in this equation is the wave speed, and US is the speed of the source. Now again, similarly, this is actually the speed of the source along a line of sight. So it's not quite so simple as it might seem. It's the speed of the source along a line of sight. Okay. So it's a little bit different if the source is not moving directly towards you or away from you. You have to be a little careful with that. Now, the other thing to be careful about, there's a plus or minus here. Which one do we use? Well, you got to think about it. And here's how you got to try to figure it out. So let's say that we have a source that's moving toward the observer. If we have a source moving toward the observer, then the frequency should be greater than the emitted frequency. In order for the observed frequency to be greater than the emitted frequency, then this thing in the parentheses has to be greater than 1, And for that thing to be greater than 1, then the denominator has to be smaller than the numerator. And if the denominator is smaller than the numerator, then we have to use the minus sign. Okay, now let's say we have a situation where the source is moving away from the observer. If the source is moving away from the observer, then let's see. If it's moving away from the observer, then the frequency should be smaller. And if the frequency is smaller, well, then that means that this quantity in the parentheses has to be less than 1. In order for that to happen, the denominator has to be bigger than the numerator, which means we have to use the plus sign. Okay. All right. So it takes a little bit of justification. It takes a little bit of thought to determine whether or not to use the plus or the minus sign. Now let's go over to the equation for a moving observer. If we have a moving observer, then f prime is equal to f times v plus or minus u0 or uo divided by v. You can guess what these mean. F is the frequency of the emitted wave. F prime is the frequency of the observed wave. V is the wave speed, and uo is the speed of the observer. And now whether we use a plus or minus sign. Well, let's say we are moving toward the source, an observer moving toward the source. If the observer moves toward the source, well, then the frequency that's observed should be greater. And if the frequency that's observed is greater, then that means this thing in the parentheses has to be greater than 1, which means that we need to use the plus sign. All right, now let's have an observer moving away from the source. If the observer is moving away from the source, then we'd expect to observe a lower frequency. In order to observe a lower frequency, a smaller frequency, then this thing in the parentheses has to be less than 1, which means that we need to use the minus sign. And if you're wondering why IB doesn't just tell you whether to use a plus or a minus in each situation, well, they want you to think about it. They want you to go through these kinds of justifications and thoughts to figure out which one to use in which situation.